In this tutorial, I will show you how to do particle statistics analysis in SMAC. Particle statistics analysis allows you to obtain information on the intensity distribution of elements within individual particles and to be able to compare across these particles. That is, we're going to define which areas of our image comprise particles and which comprise background. We will ignore the signal in the background, allowing us to focus in on each of the particles. We can also obtain the distribution of particle sizes, and we can compare whether different particles have distinct chemical compositions using ANOVA. So let's begin by first opening a file. I'm going to go ahead and choose this one and hit open. So let's click on our calcium channel, and I'm going to do 2 image processing steps before we begin the particle analysis. So first, let's right-click on the image and click edge removal to get rid of bad pixels on the side of our image. And then we're also going to go ahead and go process, advanced filtering, and blur. And I'm going to blur the channels that I'm interested in analyzing. In that case, this is calcium, potassium, and also silicon. Choose a filter size of 5 and a standard deviation of 0.8. These are my preferred settings. And click Save and Done. So in 2 additional tutorials, we cover blurring. I'll just say here that I like to do blurring before pretty much any of my image analysis steps that I perform because it helps to reduce the impact of noise on the analysis. So these are the 3 images that I come up with. Okay, so we're going to begin the particle statistics analysis by assigning which areas in the sample are particles. To do this, we're going to select Threshold from the process menu. This brings up this new window. So thresholding will allow us to assign what features in the sample are particles and which are part of the background. So first we're going to choose a channel on which to do our thresholding. There are different algorithms in SMAC that allow us to do this thresholding. The ones that I like to use are inverse binary and also Otsu. So let's start with inverse binary. Select inverse binary, and now we also have to select a threshold level. So what this threshold level means is that any pixel with an intensity less than 50% of the highest intensity pixel in your entire map is going to be assigned to be background, and it will be ignored by the particle statistics analysis. Any pixel that has an intensity greater than 50% of the most intense pixel in your map is going to be assigned to a particle. So let's see what happens if we take a threshold value of 50%. Just click preview, and you can see that your image turns to blue. That means that you're actually thresholding out all of the particles in your sample. So let's push this lower. For many samples, a threshold around 10% often works pretty well. Let's see what that does for us. Preview, we still see no particles, so we're going to have to push this threshold level down. I'm actually going to go all the way down to about 1.20. Hit preview, and now you see in red, those are the pixels that are assigned to be part of a particle. And just looking at these, it looks like I'm getting a lot of the pixels, or a lot of the particles that I can see present in my image based on what I remember of the calcium intensity. So I'm going to go ahead and click Save and then Done to get out of this window. Now let's scroll down, and you can see that I have a new data channel called Calcium Blur Thresh, and that's this thresholded data channel. So let's go ahead and see how it compares to our calcium intensity. To do that, I'm going to go ahead and right-click on my calcium blur channel. Right-clicking brings up a new display. I have to perform edge removal again on the new display. But now you can see by comparing the threshold in the image display that I am assigning most of the particles that I can see myself as having high calcium signal to be particles in my threshold channel. Okay, so let's look at what the Otsu thresholding does for us. So we're going to go back to process, go back to thresholding, select our calcium blur again, and now we're going to click Otsu and click preview. And you see that we actually have a few more pixels identified as being part of particles in this image. And it's really up to you to choose which of these types of thresholding you want to use. I recommend playing around with this, perhaps trying the particle statistics analysis using both different types of thresholding, and then comparing your results at the end and seeing which of these is actually a more reasonable representation of your data. I should say that the way that Otsu works is actually very similar to inverse binary, except that it's more automatic. So Otsu makes a histogram of the particle intensities in your image, and then it has an algorithm to find the threshold below which it throws away any of those pixels and assigns them to be background. And so that's sort of what's happening in the background when you click this Otsu button. So unlike inverse binary, there's no thresholding level that you need to choose. You simply click Otsu. Again, I'm going to press save, and then I'm going to press done. So before we do the particle statistics analysis, we have one more step, and that is to assign the minimum number of pixels that make up a particle. So for this, we're going to go Analyze, Set Minimum Particle Pixels. This brings up this new box. And now what this does is any particle that's found in your threshold window that comprises 2 or less pixels is going to be assigned to be background. So this gets rid of noise, artifactually high pixels that are present in your image. I'm going to set this minimum pixel area at 2 for right now, and click OK. So now to do the particle analysis, you want to select the threshold channel that you want to work with. So thresh 1 was the Otsu. I'm actually, in this case, I think I want to stick with the inverse binary. So I'm going to select calcium blur thresh. I'm going to go to Analyze and Particle Statistics. When it's done calculating, you'll have this new window called Particle Statistics. So the first thing that you see is a set of tabs here. So you have individuals, distributions, box plots, and ANOVA. We're going to start with the individuals tab, which gives you just a table with a list of all the particles that you've identified. So the first column just gives the file name. The second gives the ROI. ROI stands for region of interest, and that is the particle. So let's move this over. You can actually click on a region of interest, and then you can click down here and say show current, and it will actually highlight that particle on the map. You can click through these, and we can see that as we click through all of the different regions of interest, we're highlighting different particles. And so this is an easy way to figure out, okay, region of interest 14, that actually corresponds to this, this particle on my map. Additionally, you have columns for the number of pixels. So npix, number of pixels that comprise any one particle, you can multiply this value by the pixel size in order to get the area of your particles. Finally, you have X center and Y center. This is the horizontal and vertical coordinate for the center of the particle. So you can view the intensity information for each region of interest by highlighting the element channel under Select Channel. So go here, scroll down. We might want to look at calcium. So let's click calcium and wait. There we go. So whenever you click one of these channels, it's going to actually calculate the intensity values for you. And so it's going to take a second, and you'll just have to wait a little bit until the table updates. So right now, we're looking at a column of calcium intensities. What exactly are these intensities? Well, they're the sum of all of the intensities present in the pixels in that particle. It's often more helpful to actually look at the mean. So if we select mean instead, you can see that this value updates to give you the mean and we may want to look at the standard deviation. Okay, now you see the standard deviation. You can select a number of channels at once just by control left clicking or shift left clicking. So let's go ahead and select silicon and add that to our table. Great. And now you can see those values are listed here. We also have the possibility to add correlations by clicking on. And when you do that, it's going to show you the ratio of the two elements that you've selected based on the slope of a fit line of a correlation plot of the intensities of those two elements within all the pixels that are part of that particular particle or ROI. When you're happy with this table, you can export the data so that you can manipulate it in another plotting program. So when you click export data here, that's actually going to put it onto your computer's clipboard, and then you're just going to paste, so Control or Command V, into the plotting program of your choice or a text editor file. The next tab over is the Distributions tab. The Distributions tab gives a histogram of either the area, the concentration, or even the correlations of the elements listed in your Select Channels window. So a histogram plots the value, so either the area or the concentration on the x-axis, and then it plots the frequency with which particles that have that area or that concentration occur. So let's look at concentration for calcium, and I actually prefer to have a greater number of bins. I often use about 100, and let's hit update to update that plot. So you can export this plot by hitting export. So another way to view the distribution of intensities across all regions of interest for each element is using a box plot. So let's click on the box plot tab and see what that gives us. So this is showing us the range of intensities for an element, the element that's selected here under channel, as a function of ROI. So this axis actually lists the ROI number. Unless you have very few regions of interest, it's a little bit hard to read this axis, but each tick mark is a different ROI. So you have ROI 1 through 26 in this instance. So on this this plot, the orange line is representing the median of the pixel intensity within each ROI. The box represents the lower and upper quartile of the pixel intensities found in that particle. The line represents the range, and the crosses represent outliers. I think that this is a pretty easy way to compare pixel intensities across the different ROIs for your different elements of interest. So I actually like looking at these plots. I think it's pretty useful. So for instance, I can say, okay, particle 26 has a really high calcium content. Let's click on silicon, and it also has a high silicon content. If we look at potassium, it sometimes takes a few seconds to update, also has a high potassium content. Let's go back to calcium again. You can also see that these two ROIs right here have moderately high calcium intensities. If we look at silicon, we can see that they're also silicon hotspots, and they have a little bit of extra potassium in them too. So it's a pretty easy way to get a good handle on which of your particles is containing a lot of one element versus another. You can save this plot as a JPEG if you hit Save Graph. Finally, the last tab has the ANOVA analysis. So this allows us to examine whether different ROIs exhibit significantly different intensities for the particular element. So you want to select the channel that you're interested in, And then all you're going to do is go ahead and highlight the ROIs you're interested in, and they're automatically going to populate in this window. So let's make this a little bit larger so we can see what's going on more easily. So these are color coded, as you can see. And what this is telling you is that ROI 3 versus ROI 5 are significantly different at the p less than 0.005 level. In contrast to ROI 8 versus ROI 9 is significant at less than 0.01. ROI 1 is different than ROI 4 at the less than 0.05 level. And then if we scroll down here, you can start seeing particles that are not significantly different from one another. For instance, ROI 7 versus ROI 8 only have a p-value of 0.029, so that's not significant. Okay, so those are the 4 types of analyses you can do with the particle statistics package. When you're done analyzing your particle statistics data, you're going to just go ahead and click Done to get out of this window. So note that if you want to reopen the particle statistics package, SMAC will redo all of the calculations. You'll come up with the same calculations, but this can be a bit time consuming, so I recommend saving and exporting the data that you want before you click Done to get out of this. So that's particle statistics. But in addition to particle statistics, we also have a module to perform masked statistics in SMAC. So this is the same idea, but instead of using thresholding to identify particles in your image, you're actually going to use masking to define different regions in the image on which you want to obtain statistics. So let's see an example of this. In other tutorials, we've covered multiple ways to make masks. I'm going to show you one way here that's particularly useful, and then we'll do the mask statistics on it. So I need to let you know that in this particular sample, what I'm really interested in is whether particles that contain calcium also contain silicon and vice versa. So I'm interested in discriminating among particles depending on their calcium to silica ratio. So what I'm going to do first is use MapMath to make a new channel that gives the ratio of calcium to silicon. So I'm going to go down here and I'm going to take calcium, I'm going to divide it by silicon. I'm going to do this calculation and save this calculation. Now I have my new channel, which is shown here. Okay, so now I'm going to do a clustering analysis that's going to group the pixels in this image based on their ratio of calcium to silicon. So I'm going to try to group pixels together if they have high calcium to silicon ratios, and other pixels together if they have low calcium silicon ratios. And then I'll have a couple intermediate ratios in between. So to do this, I'm going to click PCA analysis. And again, PCA analysis is covered in a separate tutorial. I'll just give one example of how we can use it here. I'm going to select the calcium to silica ratio channel, and I'm going to select K-means. K-means is a type of clustering algorithm, and this clustering algorithm is going to group the pixels in my sample. I can choose the number of clusters. I'm going to choose it here to be 4. So the number of clusters is the number of groups. When I say that I want 4 clusters, what I'm saying is that SMAC should make 4 different groups of pixels that are alike one another in terms of their calcium to silicon ratio. Click OK. Scroll down. I have this new channel called K-means clusters 1. If I click on it, all of the yellow pixels have similar calcium to silicon ratios. All the light blue have another calcium to silicon ratio, which is different than red, which is different than dark blue. So now that I have this K-means clusters window, I'm actually going to make a set of masks out of it. To do that, I'm going to return to my map math window, and I'm going to scroll down and hit k-means clusters 1, and then I'm going to hit 2 to the x, and then I'm going to call this k-means mask, and I'm going to do the calculation and save the calculation. It looks the same, SMAC updated the colors, but what has gone on in the background is that you've actually converted the k-means clusters into a set of masks that we can now do the mask statistics on. So to do that, let's go back to the Analyze menu. We're going to drop down, select Masked Statistics. And now you see that we pull up the same window that we had before for the particle statistics, but now we only have 4 ROIs, and each of the 4 ROIs corresponds to our different k-means clusters. So let's show the current. So the orange is ROI 1, now it's ROI 2, now it's ROI 3, and now it's ROI 4. So I can go ahead and just like before, I can go and look at my calcium intensities for each of those different clusters. I can add silicon to that, update it, and now I can very easily see the calcium versus the silicon content in all of these different masked areas. I can also go to box plots, and now I can compare the calcium intensity across the different masked areas versus the silicon intensity in the different masked areas. Again, it always takes a minute to update these plots. And that's the potassium. So now we can go ahead and click Done to get out of that. And that is how you use particle and mass statistics in SMAC.